everybody. Nice to see you all again. We are talking about integration by parts. I had just a few more things to say about that, and then we'll go on to a new something. The homework for this week is just about parts, due tomorrow as always. But the quiz, I didn't put the L'Hopital's rule on the quiz last week, so the quiz will include L'Hopital's rule and the parts stuff. I hope that's not too confusing. I'll remind you again later on. I hope you've been keeping up with your quiz scores. You can see them on Gradescope, of course. Please let me know when you want to reattempt some of the old ones. We'll do them. Okay, let's just refresh our memory. The integration by parts, everybody needs to know the integration by parts formula is this. Integral of u dv is uv minus integral v du. And this you should, I suppose, memorize eventually. Once you do enough of these, hopefully you will naturally remember that it's not that complicated, the formula. Integral of u dv is uv minus integral of v du. Let's just do a little warm up to make sure everybody remembers what we're talking about here. Parts, integration by parts is typically used when you see multiplication on the inside of the integral sign. Like in this case, I have x times e to the 4x. And you have to know how to choose the parts. You see the two parts are the two things which are multiplied together. In this case, one of them is going to be x and the other is e to the 4x. And as we discussed last time, you want to choose the u part to be something that gets simpler when you take the derivative, and the dv part to be something that gets simpler when you take the antiderivative. By simpler, I mean like maybe it gets simpler or maybe it just stays the same. In this case, I'm going to choose u to be x. When you see if one of the parts is a polynomial, like a power of x, then usually that's what you want to choose to be the u. This is pretty much always true unless the other part is a logarithm. If you see a log, you definitely want that to be the u. Anyway, that's the u. The dv then has to be e to the 4x dx. That's the other part. And then, so those, I just chose them on my own. Sometimes, it's possible to make the wrong choice and you'll see that you get stuck in the next step and then you have to go back and choose it right. Anyway, the next thing that I do is I figure out what is du and what is v. So du is, just like in a u substitution, it's the derivative of the u, which in this case is going to be 1 dx. It's just dx. And then v is the integral of dv, which in this case is, I don't know if I ever said this specifically last time, but this is actually something that comes in handy when you're doing these integration by parts formulas. If you have e to some constant times x, the integral of that is 1 over that constant and then times e to whatever. This is actually, maybe I'll put this sort of in a little red sidebar. These are helpful things that come up when you're doing integration by parts often. The integral of e to the kx, if k is any constant, is always 1 over k e to the kx. It's because the derivative of e to the kx would be e to the kx times k. That's the chain rule. So when you take the derivative of this kind of thing, you multiply by k. That means when you take the antiderivative, you have to divide by k. It's the opposite. Plus c, of course, if you like. And there are similar things. I will just mention them now because these will come up every so often. If you have sine or cosine with an extra constant on the inside, if you were taking the derivative, the chain rule would say you have to multiply by that constant, but since I'm doing the integrals, I'm going to divide by that constant. So the integral of sine of kx is 1 over k. Well, it's negative because the integral of sine is negative cosine. Like that, right? And then there's one for cosine also. 1 over k sine kx plus c, like that. These will come in handy every so often. So the first one there is what I just used here to find the dv, right? E to the 4x, the integral of that is 1 over 4 e to the 4x. All right, anyway, let's finish the integration by parts. So here is my various parts. It is just so that we remember, uv minus integral v du, right? So this becomes x, just plugging everything in. U is x, v is 1/4 e to the 4x minus integral v is 1/4 e to the 4x, and du is dx. So you just plug in all the bits where they go. And now there's still an integral to do. We have to do the integral of 1/4 e to the 4x. Usually you want to simplify that as much as you can before doing the integral. There's not much to do here. We can just pull the 1/4 out of the integral sign. It's probably the best it'll get. So 1/4 x e to the 4x, that was there before, and then minus 1/4 integral e to the 4x. And then what is integral e to the 4x? Again, it is 1/4 e to the 4x. So this is pretty much my final answer. 1/4 x e to the 4x minus 1/4 times 1/4 e to the 4x. Like that. I again used that first rule in the red box there. E to the 4x becomes 1/4 e to the 4x. Right? Any thoughts about that one? This is just a warm-up, very much like the ones we did last time, although I'm using that e to the 4x rule. All right, great. So I have two matters to discuss concerning the parts. Really, it's maybe just one. One thing that we didn't talk about last time is, what if you have specific values in the integral? Like these have all been what we call the indefinite integral. That's the one where there are no little numbers here and you just put the plus c at the end. What about the definite integral? That's the one with the little numbers. How do we handle the definite integral? You'll see there's not much to it, but I thought we should just do at least one example like that. How about integral from 1 to 3 ln x over x squared? So I'll just write in words what I'm about to do here. So when we have values to plug in, I'm referring to the 1 and the 3. I will say it this way: do the whole integral by parts. Plug in for all the x's at the end. All right, so I'm just going to sort of ignore the 1 and the 3 for now, and just hopefully I won't forget them at the end. So at the very end, instead of putting plus c, I'm going to put that bar with the 1 and the 3 and then plug the numbers in. All right, and there's really no funny business that can occur, although we might as well talk about it at least once. So ignoring the 1 and the 3 for now, let's try and do the parts here. Now, first of all, these what I see inside the integral is written as a fraction, but I'm not into that when I'm doing integration by parts. It must be written as a multiplication. Anybody have a suggestion? How can I write that instead as a multiplication? Yeah? Yeah, I like that. X to the negative 2, she said. Dividing by x squared is the same as multiplying by x to the negative 2. So this is, let's just forget about the 1 and the 3 for now, like I said. X to the minus 2 ln x dx. All right, and now I'm going to do the parts. Those are my two parts, x to the minus 2 and ln of x. What shall I pick for the parts? U and the dv. The u should be something that I like to take the derivative of. The dv shall be something that I like to take the integral of. What about ln of x? What do you think? Should that be the u or the dv? Yeah? It should be the u, yeah, because the derivative of ln x is 1 over x, which is not so hard to deal with. The integral of ln x is not anything, it's something like x ln x minus ln x. It's something weird like that, which I'm not into that. So I'm going to put the u as the ln x. That's because du is 1 over x, right? And then the dx, of course. And then the dv must be the other one, which is x to the minus 2 dx. You always include dx as part of the dv. And then the integral of that is the v. Can anybody say what's the integral of that?
It
Yes, negative x to the negative 1, she says. I like that. Remember, for this, you would increase the exponent by 1, so minus 2 becomes minus 1. Then you divide by the new exponent, which is the same as just putting a minus sign in front. Excellent. All right, these are my parts. So I say my parts formula, uv minus integral v du, is ln x, that's the u. V is negative x to the negative 1 minus integral v negative x to the negative 1. Du is 1 over x dx. So that's just plugging everything in for my parts formula. Let's simplify as much as we can here. We do have to do that other integral now, but it's just powers of x in there, so it should be fine. What I got in front is minus x to the minus 1 ln x, and then minus, actually, can I say plus? Because there's a minus sign inside the integral, which I'm going to bring out. So plus integral x to the minus 1 times 1 over x. Can we simplify that? I believe those can combine somehow, or maybe they cancel out, or whatever. Any thoughts? What does it end up being? Yeah? 1 over x squared, she said. Yeah, I think it's actually more convenient to write it as x to the minus 2, which is the same, because I'm going to do the integral of this in the next step. But that is the same as 1 over x squared. It's because x to the minus 1 is the same as 1 over x. So the way I would think this through is write this 1 over x as another x to the minus 1, and then you multiply them together by adding the exponents. It ends up being x to the minus 2. Great. And then finally, I do the integral. So again, integral of x to the minus 2 becomes minus x to the minus 1. The same integration that we did in the previous step. And now, finally, instead of writing the plus c, I put the bar with the 1 and the 3. And these values get plugged in everywhere. So what can be sometimes a little confusing is you might think that the values only get plugged into this part because this part is inside the integral, but it's not so. The values need to get plugged in everywhere here. It's really because whatever the answer is, like this being a definite integral represents the area under the curve, the answer better be a number. There should be no x's left over in your answer. The answer has to be just a plain number. So it means you must plug these values in throughout the whole thing, not only on this second piece there. All right. This is what I said. Do the whole integral by parts. Plug in for all the x's at the end. So my final answer is I plug in the 3. So this is going to be minus 3 to the negative 1 ln 3 minus 3 to the negative 1, and then subtract and plug in the 1. Minus 1 to the negative 1 ln 1 minus 1 to the negative 1. And that's that. I'm sure you could simplify this a bit. Ln of 1 is 0, so that part can go away. All those minus 1 powers are the same as like 1/3, but whatever. All right, this is how we do parts with the little numbers. There's no trick to it. You just have to know how to do it. I got one for you all to try, just to make sure everybody's feeling good about this. Let's try integral 1 to 2 of 1 minus x squared e to the 2x dx. How are you going to handle e to the 2x? This is one of those times when you will want to use this rule. Integral e to the kx is 1 over k e to the kx. So you're going to use that where k is 2, but I'll let you see how it goes.
this is correct. Yeah. Gotcha. Gotcha.
Okay.
Yeah.
I would say try and simplify this stuff before. This is multiplied, so this is 2, you cancel it. How's it going? Work that out. This is not a good step. So you have these 2 different pieces, you can't just do the integral of each piece separately. That's not allowed in an integral. Like, actually, you should, if that were allowed, you should have just done that. The appropriate thing to do here is ports again. Doing all right?
Everybody seems to be doing all right. I'm gonna start writing my answer.
Are we into like the entire thing? Do parts twice?
Yes.
Okay.
Yeah. The answer has to be a number, so you can't leave any x's like x's. They all have to become numbers. All right, can we talk about this? I don't know if everyone is completely finished, but we can finish together if not. So this is what I get when I did the parts the first time. I pretty much everybody got that. We should try to simplify inside the integral sign there. What I see is this 1/2, this is all multiplication here, so we can rearrange the order however we like, and that 1/2 can cancel the 2. I also have a minus sign, which I'm gonna pull out of the integral, and so it's gonna be, this business out front is just the same, plus integral. I have e to the 2x times x dx, right? It's a plus because I had a minus sign inside, which I brought out of the integral. And now how do I handle e to the 2x times x? We do parts again. So the parts for the second time shall be x, and dv is e to the 2x dx. So du is just dx, and v is the integral of that, which is 1/2 e to the 2x. So we got this thing in front is just going to stay like that forever. Plus, and now I do uv minus integral v du for my new parts. That will be x 1/2 e to the 2x minus integral 1/2 e to the 2x dx. Right. Now we have to do that inner integral, pull the 1/2 out, and then do the integral of e to the 2x will again be 1/2 e to the 2x. So after doing all of that, I end up with 1 to the 2x plus another 1/2 x e to the 2x, and then finally minus, it's now going to be 1/4 e to the 2x. That's because there was a 1/2 before, but then I'm doing the integral again, which gives me another 1/2, and they multiply together to be 1/4. And this is the end of all of the integral signs. Ordinarily, I would put the plus c here, but actually we have values to plug in. They were 1 and 2, so I put the bar with the 1 and the 2, and now we plug those values in for x everywhere. So I'm not going to try to simplify this, but it's 1 minus 4 1/2 e to the 4 plus 1/2 2 e to the 4 minus 1/4 e to the 4. I guess I multiplied all those 2 times 2's equals 4. And then minus, go through the whole thing again, plugging in 1. So it's 1 minus 1 1/2 e to the 2 plus 1/2 times 1 e to the 2 minus 1/4 e to the 2, like so. All right. I hope you all got something like that. I mean, it seemed to me that pretty much everybody was on the right track, at least. Any questions about that one? Excellent. Great. Okay, I have one more weird example of the parts, and then we'll go on to talk about something completely different. So, one last example. This is a weird one. Sometimes you have to do some weird, funny business. E to the x times sine x. This is one last integration by parts example. So the fact that we have multiplication in there means you should be thinking about integration by parts. Sometimes multiplication can be handled with just an ordinary u substitution, but in this case, this one cannot. The e to the x and the sine x are really totally different things, which we should consider as two separate parts. Now, in this one, actually, there's not a very like cut and dry decision about what should be the u and what should be the dv. Generally speaking, I want the u should be something that gets simpler when you take the derivative, or maybe stays the same. But actually, both of those, e to the x or sine x, they both kind of stay the same. I mean, e to the x, like straight up, does stay the same. Sine x becomes cosine, which is not exactly the same, but more or less the same as far as I'm concerned. In this problem, actually, it doesn't really matter which way you choose. It's going to work out the same way either way. But I'm going to pick u equals sine x just because that's how I did it on my paper. E to the x dx then will be the dv. All right, so somebody say, what's the du? Cosine x, yes. Thank you for the shout out. And then the v, that'll just be e to the x. I should put dx goes inside the du. And the v is e to the x. Okay, so do my parts here. uv minus integral v du. Hope it's not annoying that I say that over and over again. I'm trying to burn it into your memory cells. Sine x e to the x minus integral e to the x du is cosine x. All right. Okay. It looks like we're going to have to do it again, although to be honest, I'm not feeling terribly good about this because when I do it again, I like to feel like I'm getting somewhere. Like for instance, in the previous example we just did, we had to do it twice, right? But I actually feel pretty good about doing it again in this case because I began with one of my parts is like a x squared, but in this case, my part is just a x to the 1, and I can anticipate in the next step the x will go away entirely. And this is how it usually goes when you do it again. In this case, I'm not so sure that this is actually going to get any better if I do it again, because the sine turned into a cosine. If I do it again, this is going to turn back into a sine or something. Like I'm not convinced that this is going to work out. But like I said, this is a weird one. So I am going to do it again. You'll see something kind of weird happens. So we are going to do it again. And I am again going to choose u to be the trig part and dv to be the e to the x part. All right, so that means my du this time is negative sine because that's how sines and cosines works. And then the dv, the v is again just e to the x. All right, this is my parts the second time around. And so this thing here is going to become, all right, I have sine x e to the x, that's the part at the beginning, minus. And here I do my parts formula again, uv minus integral v du. So it's cosine x e to the x minus integral v du, e to the x times negative sine x dx. All right. Can we simplify it all? Maybe I'll just handle the minus signs. So those two inner minus signs here, this minus sign can come out and make a plus, but I'm going to distribute this minus sign also. So it'll make this a negative. This will actually end up being negative again. So if we distribute all the signs properly, and maybe I like writing e to the x first, that really doesn't matter, but minus e to the x cosine x. This is going to be minus integral e to the x sine x. All right. I'm distributing this minus sign here, which would make it a plus, but I have another minus here, so this is a 3 minuses make a minus. All right. And now I am, remember where we started? Maybe I'll just, can I squeeze that in over here? Where we started was e to the x sine x, right? dx. And apparently it equals that stuff. And what I really dislike about this is I ended up with what I started with. I did 2 steps and got precisely nowhere. We are exactly back to where we began. Not a good sign. But we can kind of snatch victory from the jaws of defeat, as they say. Anybody have a somewhat weird idea? You can actually use this to our benefit here. Anyone? Anyone got weird notions with this? There's something weird you can do here that lets you actually finish the whole thing. Check it out. This is the same as that, right? But it has a minus sign in front of it. And what that means is I can add this to the other side, and there is now 2 of them, all right? So we are going to, this is a weird step, but I'm going to add this integral on both sides, all right? So I add this to both sides. Of course, it cancels out on the right side, but on the left side, there's going to be 2 of them now. And so it'll say 2 integral e to the x sine x dx equals e to the x sine x minus e to the x cosine x. All right, and how about divide by 2? So integral e to the x sine x dx is, divide by 2, I'll write as 1/2 times e to the x sine x minus e to the x cosine x. The end. This is the answer, right? That was the whole point of this was I was supposed to figure out what's the integral of e to the x sine x, and that's what it is. Very strange way of evaluating an integral by like moving it around and solving for it. I suppose, just to be technical about it, you should put in a plus c, and it's a little weird about like in which step precisely does that plus c arise. I think it's probably right here, and then we rearrange a little bit, but we don't need to get into that. But this is a very weird example. Sometimes you can do the integration by parts a few times, end up with what you started with, and then sort of solve for the value of the integral. Strange but true. All right. Any thoughts about that one? All right, great. This is not a typical integration by parts formula. That's a weird one. I think this is all I want to say about the integration by parts. Really, the only new stuff that we did today was just the plugging in the values. All right. I don't know if it's out of turn for me to say, but I kind of feel like integration by parts is sort of an easier topic. You know, of all the topics that we do over the course of the semester, some of them are kind of harder ones, some of them are easier ones, in my opinion. To me, as long as you can remember the formula, the integration by parts, I feel like is maybe even a little easier than a U substitution. This is my own personal opinion. Unfortunately, The next topic or two that we're doing is, in my opinion, one of the hardest ones that we're going to talk about for the semester. So get, I don't know if that means anything to you, but get ready for something. What I want to talk about for now is what we call trigonometric integrals. Trigonometric integrals. Trigonometric integrals, and there's the next topic is called trigonometric substitutions. So these are two different, although very closely related, tricks for doing integrals. All right. So far, we don't have very many tricks at all. We have the u substitution and the parts really are the only integral tricks that we have. But these are going to be some more integral tricks. Trigonometric integrals and trigonometric substitutions. They are both kind of weird types of u substitutions, basically. They're kinds of u substitutions that you would never really think of to do on your own, but once you see it, you can learn these tricks. So this one in particular, trig integrals, this is about things like integral of cosine to the 4x times sine cubed of x, something like that. All right, so they are products of powers of sine and cosine. This is basically what trigonometric integrals are about. Products of powers of sine and cosine, or sometimes just sine and cosine on their own, like the integral of cosine to the 4 of x. That would be something you do using a trigonometric integral. All right. These involve using some slightly obscure trig identities. So these tricks are based on, well, the one that we're doing today is kind of a little easier than the one we'll talk about next time. Yeah, maybe we'll get to it this time, I don't know. But anyway, let's talk first about a trick based on everybody's favorite trigonometric identity, which is sine squared plus cosine squared equals 1. You probably learned a bunch of weird formulas about sine and cosine in your youth. This is the most important of all of them. And this is really the only one that I sort of have like permanently memorized in my brain. When I'm working with sines and cosines, sometimes I remember that the other ones, there's lots of other formulas that I know they exist and I go look them up if I have to. This one though is something that comes up so often that everybody knows this one. Anyway, this is a trick based on that. This, as far as using it in this trick, it is more often written in this way if you solve for one or the other. So sine squared of x is 1 minus cosine squared of x. That's just rearranging that formula. Or sometimes you want to do it the other way around. Cosine squared is 1 minus sine squared of x, right? For the trick that we're going to be talking about today, it's more useful to write it in those two ways. Let's just try a simple example. How about, this is the classic kind of fairly easy one of this type, trigonometric integrals, cosine cubed of x. All right? There is not a nice, cute formula for this. It's something that you have to figure out by doing some kind of weird u substitution, and that's what we're going to be doing here. So this, just before we get into any business here, just so that everybody is clear, that means this. This is a weird way of writing things, but it's very standard. I mean, it's not abnormal for people to say it this way. But it is, in my opinion, a strange way to write it. Cosine cubed of x, what that means is this, all right? It means cosine of x, the whole thing cubed. If it were up to me, I would say this is a totally stupid way of writing it, and you should always write it this way. But actually, in real life, lots of people write it this way. So who am I to argue with lots of people? But anyway, that's what it means. And here's the trick, all right? I will say, basically, we want to do a u substitution, u equals cosine x, because that's like the thing on the inside, right? And when I'm doing u substitutions, I usually choose the thing on the inside to be the u. But it's not gonna, it won't work in this example. But in that case, the du would be negative sine x dx. And I don't see the du here at all. There is no sine x part of that. And so this particular u substitution is just not going to work because it requires there to be an extra sign in the integral, which there isn't, all right? So I'll say du equals minus sine x dx, but I don't see any sine x in there. And this is the problem, right? It's all cosines. If there were some mixture of sines and cosines, I would actually feel better about that, because then at least maybe it seems more reasonable that I could make some of this u substitution work. And here's the trick. The trick is, I call this is my fairly uncreative name for this trick, the save one trick. I'm going to save one cosine and then rewrite the others. Here's what I mean. So what I begin with is cosine of x cubed, right? I'm going to save one of them as a cosine and then put the others as a cosine squared. So I write this as cosine squared x times another 1 cosine x dx. This is the one I saved. You save one of them, and then what do I do with the other one? The other one I rewrite like up there. Cosine squared is 1 minus sine squared. The effect of this is I get a mixture of sines and cosines, which, like I said, is actually better for the purposes of doing a u substitution. So I go here, write the cosine squared as a 1 minus sine squared. All right. And now I do what is admittedly a weird u substitution. So now I go u equals sine x, not sine squared and not 1 minus sine squared. This is slightly weird. This is, like I said, it's just a u substitution really, but it's weird and it's not the kind of thing that you would come up with on your own. But once you see it, you can fairly easily replicate this trick in other examples. U equals sine of x. That means du is cosine x dx. And I can plug into everything here. It will say 1 minus u squared times du. And now this is a very easy integral to do, because it's just a polynomial with u's, all right? It all worked out. Who would ever think of doing this? I don't know, but really it only took one guy to think of doing this, and now that we all know how to do it, you can do this in many other examples, all right? So anyway, just to finish it off, 1 minus u squared du, I do the integral. Using u as the variable, 1 becomes u, negative u squared becomes minus 1/3 u cubed plus c. And then for my final answer, I plugged back in the u's. You can see at the top there, u equals sine x. So my final answer is sine x minus 1/3 sine cube x plus c. That's it. All right, it's a weird trick, but it's not so hard to do if you know what's up. When you see a power of one of these things, you save one of them, and then the other one you rewrite in terms of the other trig function. All right? Let me just try and describe in words the basic idea here. So you save one cosine, and then write the others in terms of sine. And then you do u equals sine x, du equals cosine x dx. All right, that's really the whole trick. It is a strange but really fairly simple idea. Not the kind of thing you would come up with on your own, but it's not so hard to do if you know what you're doing. All right, and sometimes you want to do it the other way around. So in this example, I saved one cosine. Of course, if you started with all sines, you would save one sine and then write the others in terms of cosine. So I would say, or, vice versa. I mean, save one sine, then write others as cosine. And then the substitution you would do would be u equals cosine x, du equals negative sine x dx. It works exactly the same. You just do it the other way around. All right. Can we think about in what situations will this actually work? It turns out this doesn't always work. It works when the power is odd. So here I had cosine x cubed. I save one. The rest is cosine squared x, which, lucky for us, we can rewrite in this format because it was a cosine squared. If it was a cosine to the 4, actually you could do this also. It would just be this thing, the whole thing squared. Anyway, it requires that the power be odd, though. If the power was even, then you'll save one of them, and the rest of it will be an odd power, and you won't be able to do this same trick to it. So I will just say, I can do one more example, and then I got ones for you to try. So this works in something like integral of sine to some power x times cosine to some power x, when at least one of these powers is odd. If they're both even, actually it requires another weird trick, which probably we'll get to next time. But we are also going to talk about that. But for now, this trick, the save one trick, works when at least one of the powers is odd. You save one of the odd power. All right, let's just try another one. How about integral of sine squared x cosine to the 5x? All right. So first of all, I see powers of sine and cosine, so I know this is going to be one of these weird trigonometric integrals. And the cosine has a power of 5 and the sine has a power of 2. I'm going to choose the cosine to save one of, because like I just said, this trick, generally speaking, only works with using an odd power. So I am going to save one cosine here. So this I write instead as sine squared x times cosine to the 4x times one cosine that I leave off to the side. That cosine over there is going to become my du. And then what do I do about cosine to the 4? Well, cosine to the 4 is the same as cosine squared to the squared. So this is sine squared x cosine squared x squared, right? This is one other sort of little trick that you need to do. And then what do I do with cosine squared? That is 1 minus sine squared. This is why you need an odd power to start with. If you have an odd power, then you save one. This becomes an even, and then you can do this kind of a thing to it. If that were an odd power, I would be stuck at this point, but it's not. So now I go integral sine, sorry, I wrote sine x squared. I should have written sine squared of x. And then here I go 1 minus sine squared x squared. Like that. Strange but true. I have now saved one cosine, but then I wrote everything else in terms of sine. And now I do the substitution. And it is u equals sine x, du equals cosine x dx. So that thing at the very end is du, and then everywhere you see sine, that's u. So this becomes integral u squared times 1 minus u squared squared du. That's what we get from the substitution. And now we just have a bunch of powers of u, which I feel pretty good about. Although you can't integrate that directly, it's still weird looking. Anybody want to suggest what should we do to actually do this integral? It is just powers of u. Yeah? Yeah. You can just like square out this squaring here, do the FOIL thing, 1 minus u squared squared. You can just do the squaring. So this becomes, I have this u squared there, but now I'm going to do the FOIL there. At the beginning, we're going to get 1, and then in the middle, we're going to have minus 2u squared. On the end, I'll have u to the 4, right? That is doing the FOIL on the 1 minus u squared. And then what? Do you like this? Does this look worse to you? It is a little bigger, yeah? Yes, she said distribute the u squared. I think this is what she means, like this, right? And then it just looks like a straight up polynomial, and we can do the integral very nicely. So this becomes u squared minus 2u to the 4. You should be adding the exponents here, plus u to the 6. And now we can do the integral. Just go down the line. These are polynomials. So it's 1/3 u cubed minus 2 over 5u to the 5 plus 1 over 7u to the 7 plus c. And then finally we replace the u. Remember the substitution was u equals sine x, and so all those u's become sine. So this is 1/3 sine cubed x minus 2/5 sine to the 5x plus 1/7 sine to the 7x. That's it. Answer looks pretty crazy, but so it is a bit of a journey, I would say. To me, this is a lot harder than standard integration by parts, for example. But once you know the basic tricks, you're basically just sort of doing this trick in slightly complicated scenarios. Any questions about the steps there? I got one for you all to try. You'll see if you really get it when you try one. Let's try. So in this example, I saved the cosine because the cosine had the odd power. In this case, you would not be able to do it by saving the sine. Let's try sine cubed and cosine cubed dx. Here they're both odd, so actually it'll work either way if you save one of the sines or if you save one of the cosines. Just for fun, let's try to do it by saving one of the sines. So I will write the first step. It should be sine squared x, cosine cube x, and then times sine x dx. So I saved this one sine over there. The purpose of that is that's going to be my du eventually. All right, see if you can make it happen for the rest of it. Since I saved a sine, that means I'm going to write everything else in terms of cosine. it looks like people are doing great as I go around. You save one of the signs over here, and then what remains is only 2 signs left over, and then this sine squared, you turn it to 1 minus cosine squared. And now I do the substitution, turn all the cosines into u's. U is cosine x, that means the du is negative sine x dx. So what I see over here is actually minus du. But anyway, when I do the substitution, it becomes 1 minus u squared, u cubed, and then times negative du. This is how the substitution goes. I hope that you said something like that. And now, how do we do the integral? Well, there's a minus sign in there. I'll just pull all the way out of the integral. And then the other parts, I'm going to distribute. U cubed distributes like so. So this becomes minus, like I said, that came from the minus in front of the du. And now distributing, u cubed minus u to the 5 du. And then you do the integral. Minus out here, 1/4 u to the 4 minus 1/6 u to the 6. And plug the u's back in. Cosine to the 4x minus 1/6 cosine to the 6x. That's it. Trigonometric integrals. It's a complicated trick. Complicated to write down. I would say the basic idea of it is not so complicated. But all right. Any questions about that one? I hope, as I walked around, it looked like people were doing pretty good. All right, this, unfortunately, is the easy kind. The easy kind is when one of the powers is odd, you do this, all right? When both powers are even, it requires a separate and different trick. So let's talk about that. We got 15 minutes or so to start talking about. When both powers are even, this is a slightly more complicated trick. When both powers are even, there is another weird trigonometric identity which I don't expect anybody to remember. It is this. So these ones you should like write down somewhere. This is sometimes what they call the double angle formula, and I have the standard way of writing the double angle formula is cosine 2x equals blah 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 blah, but I've rearranged things in a weird way to solve for sine squared x in that. And then there's a similar thing about cosine. Oddly enough, it looks like this. It's cosine 2x both times. This is not a typo. All right. These are referred to as this is the double angle formula for cosine written in 2 different ways. All right. And by doing this formula kind of twice, you can get things like sine squared of 2x is 1/2 1 minus cosine of 4x. This is really just the first one, but I am replacing every x by 2x. So this x became 2x, this 2x became 4x. So this last one that I wrote is really just another version of the first one where I plugged in 2x instead of x. And then for cosine, you can do the same thing. So cosine squared of 2x is the same as 1/2 1 plus cosine of 4x. And I'll just say, etc. If you like, you could do sine squared of 4x is some kind of version of this where I plug 4x instead of 2x. All right. These first 2 are basically the ones that you will most often need to use, although we may use, actually in this example I'm about to do, we're going to use the ones further down also. All right. But anyway, let's see if we can use these. So, when both powers are even, I am referring to something like this. Let's just do this example. I think that'll do it for today, and then we'll try some more of these next time. Sine to the 4x. All right. So first of all, you look at this and say, I'm going to have to do some weird trig integral trick, but the power is not odd, which means you can't do that like save one kind of a trick. Because if I save one of these, then I'll have sine cubed left over, and there is no convenient way to handle sine cubed by using these formulas, all right? And so, instead of saving one, I am going to write this even power right away as sine squared x squared. And then use this other way of writing sine squared x at the top. And so the inner sine squared, I'm going to write like 1/2 1 minus cosine 2x. So this is integral 1/2 1 minus cosine 2x. Like that, squared. And now we do the FOIL on that squared, all right? So first of all, there's a 1/2, which is inside of the squared. That will become a 1/4, because you square the 1/2 and you get 1/4. And then the other part, you have to do the FOIL. So this becomes, maybe I'll just write that in 2 steps. Actually, the 1/4 can come all the way outside. What remains is 1 minus 2x, the whole thing squared. And there I do the FOIL. So this is 1/4 here, integral. 1 minus, the middle term will be minus 2 cos 2x, and the end term will be plus cosine squared 2x. All right. Am I getting anywhere? The answer is, I don't know, maybe. This is now an integral of 3 things added together. So at the very least, like, we can now consider these 3 things as just 3 completely separate parts. Actually, the 1, I know the integral of 1 is x, right? So that's no problem. Integral of cosine 2x, actually that is 1/2 sine of 2x. That's the thing that I wrote at the very beginning. Remember this thing? This thing. Cosine of 2x is that. All right, so that also I can handle. The only thing that concerns me a little bit at this point is the last part. So I know integral of 1 is x. Integral cosine 2x is 1/2 sine of 2x, so I can handle that. This is the only part that I don't like. Cosine squared of 2x, what do I do with that? I do this to it, all right? So you can use these rules when you have cosine of 2x or cosine squared of 2x, you can do this to it. So I am going to use that rule. This is sort of like the green one, right? That's what we do here. Cosine squared of 2x. Sorry, it's off the top. Off the heezy. All right, so this becomes, all right, I had 1/4 at the beginning, 1 minus 2 cosine 2x. Those parts I feel good about. Plus, and now I say 1/2 1 plus cosine 4x dx. Maybe I'll distribute that 1/2 there. Oops. 1 minus 2 cosine 2x plus 1/2 plus 1/2 cos 4x. And now I can do the integral of every piece of that, right? I have 4 things that are just added together, so we can just consider all of them separately. And I'm going to use, so this right here, yeah, was the green rule, right? And I'm going to use what I wrote at the very beginning of class today. Integral of cosine kx is 1/k sine kx. That's what I'm going to do each of these weird cosines there. I have one which looks like a cosine 2x and another which looks like a cosine 4x. So anyway, this becomes 1/4 out front. I'm doing the integral now. We better put parentheses because the 1/4 has to multiply by everything. 1 becomes x minus 2 times cosine 2x, using the red formula in the box there with k equals 2, 1/2 sine 2x. Plus 1/2. What happens to 1/2 just all by itself? I'm doing the integral here. Any thoughts? Yeah? It is 1/2 x. Yeah, just a constant by itself becomes that same constant times x. So 1/2 x. Great. Plus 1/2 cosine 4x. For that, I leave the 1/2 in front. And then I again do the formula in the red box. It becomes 1/4 sine 4x. The end. Plus c, right? There's actually no u substitution going on here. You're just using that weird double angle formula 2 times, I suppose. All right. To me, this is a little harder just to keep all the details straight. Although there's no u substitution, so like from an abstract point of view, maybe this is a bunch of simpler tricks, but it's a little complicated. I'll just say that. And I think we could do another one, but you can only do so many of these one after another. So I think that'll do it for me for today. We'll do some